very much for the introduction, and thanks for the organizers for inviting me to come here. It's actually the second time in a rather short time I'm in Edinburgh, but it's really nice to be here. So I like to view tensors as a resource. I want to give you a bit of an overview of a few pieces of works in the past, and maybe a bit of a vision of how I view this study could progress, and maybe give a bit of an overview and a summary on this. I think we're a small crowd. Please, do interrupt if I'm not writing clearly, or if you have any other questions, or if you want to make a comment. All right. And probably the closest piece of written stuff that's connected to my talk is our new paper on the archive. It's called Resource Theory of Tensor Networks. It's just from July here, and I'd also like to point out that there is Jeroen, with whom I've been working on this subject for many years, and I think you'll give a talk on Thursday also. So very good. Let's get started. I want to do some introduction to set the scene and to set some notation. All right, so I like to call it tensor T, and I'm generally going to think of it as just an element in the tensor product of K complex dimensional vector spaces. I might call this a multi-particle entangled quantum state and call it psi. The reason I'm not doing that, and I'm calling it T for tensor, is that I'm actually just looking at these here as vector spaces. So, I'm not necessarily putting the inner product on to make them Hilbert spaces. So tensor somehow is the more appropriate language, and it connects to a bunch of literature. I call K the order of the tensor. Some people use different words like degree dimension or anything like that, but I'd like to think of it as an order of a tensor. It's very natural to write down these tensors in components, so in like in a basis. So for that we choose bases for the individual spaces. And most of the time we will just forget about these subscripts here, okay? Just like kind of suppress them for simplicity of notation. Now, already at this level, people like to use sort of like an unwieldy object. People like to use graphical ways of representing them. Personally, my favorite way is to draw them like this, as like the dots indicating the. So this is like 1, 2, 3 up to K, and then maybe writing T here in the middle, so as to indicate this object. You'll see later how it plays in. Most people maybe would like to make a spider. So like 1, 2, up to K, and then maybe put some T on it to indicate that it's T. Some people like to use kind of like these boxes and let the legs stick out. You can interconvert all these ways of thinking about it. All right. Now this is sort of tensors. And one thing about resource theories is about comparing the objects. So the tensor is my resource. I want to, or the multi-particle entanglement quantum states, if you want to think about it that way. So I want to compare them. So I want to say when is T related to some other T prime. And we're introducing a pre-order, and this pre-order is usually called restriction. This term was already used by Strassen in the 1980s. In quantum information theory, people have this more unwieldy term called SLOCC. guess, transformation or something. Right. So we say T as LOCC transforms, or T restricts the T prime if there exists matrices M1 up to MK such that M1 tensor MK applied on T gives T prime. These are just linear maps, but what is kind of important that they're not necessarily invertible, all right? Otherwise, they would be somehow equal or equivalent. Okay, so we have our way, and now we can compare. We can compare tensors. Maybe I should say one more thing. I'm going to say that T is equivalent to T prime if T is bigger than T prime and if T prime is bigger than T. So it's kind of natural. It induces some notion of equivalence. And actually, it's now, I've been calling T above tensor, but the better way would actually be to call the equivalence class generated by this equivalence relation, T, the tensor. Okay? So I'm going to make this abuse of notation in some sense, but I don't really know how to get a nice way of doing it without it. The advantage of using this relation and these equivalence classes and realizing that this is not necessarily invertible is that the dimension doesn't play a role anymore. Okay? So somehow, you know, if T is equivalent to its embedding in arbitrarily high dimensions, so somehow I'm losing this somewhat arbitrary D1 up to dk. They just have to be big enough, and then life is fine.
Do you also put some restrictions on the m's in some cases, right? I mean, for instance, if you want to transfer tensors corresponding to probability distributions, you probably want the m's to be trace preserving or sum preserving, or more general setting. Maybe you don't.
Yeah, I think the most natural restriction now on the m's that you might put on is that you take them to be equal. You know, let's say you have like tensors that are symmetric in some sense, and then you want the m's to be equal. That would be a nice restriction. The ones that
not positively preserving or something like that.
These m's are not they're not CPTP maps. So I'm really this is just vectors, and I'm operating with linear maps on the vectors. So I'm not really in a density matrix formalism. I'm just in a pure state vector formalism plus like applying linear maps to it. Otherwise, be more complicated. All right, time for some small examples to. I don't know how to handle the boards. You want me to?
Go to the right.
I go to the right. Okay, you go to the right. Instructions of the camera is that now the camera will switch. Let's see. Go to the right. Let's do examples. So I have example 1. And example 1 is, and I'm using this tensor notation, which of course in quantum information we have our Brockhead shorthands, but I'm still going to do it. So I'm claiming that this here restricts to E0, E0, E0 plus E1, E1, E0. Okay? And then, of course, the question for the audience is, what is M1, M2, and M3 that enact this restriction? 9:30 wake-up question.
One of them is the identity?
One of them. Which one?
One maybe?
And one. Okay, that's okay. I think you should start with M3. there's one guy too many up here, so I need to chuck out one of them.
Sure.
So I'm going to eliminate E1. So I'm going to take E0 star E0. And that's going to kill this term. Okay, you can write it in the basis notation as well. What are we going to do for M2? So now I'm left with these two here. And you see that the only difference between this line and this line is that I need to make a bit flip. And now it was suggested to make a bit flip on the second one. So that this here is basically Pauli X matrix. Or you might write it now in this notation as this maybe. Very good. Time for a second example. The second example. Oh yeah, I use this example to introduce some notation. So this here is generally known as the W state from the Dervidal-Serac paper. And this here is, of course, an EPR pair on AB. Right, on the first two, tensor E0. And maybe it's a two-level EPR pair. Good. Example 2 is E0, E0, E0 plus E1, E1, E1. And I'm just going to show to you what we're going to do. We're going to introduce some formal parameter epsilon, or you can think of it as a non-zero number if you want. And we're going to observe that this is then equivalent to, so basically I change E0 into E0 plus epsilon E1. And I have it 3 times, I do it 3 times. Maybe I write it out. And then here, I'm going to map E1 to minus times E0. So this gives me 3 minus signs, so an overall minus sign. And then I get E0, E0, E0. I'm writing this equivalence here because it's easily to see that this map was invertible that I used. But it would be fine for us to just think of it as being restriction. And then I'm going to do something, it's kind of interesting. I'm just going to expand in powers of epsilon. And you see that the 0th power of epsilon is not there. The constant is being subtracted. And so I have an epsilon here. And then if the epsilon appears here, right, well, I have plus E0, E1, E0, and you know what is going to happen because you have just in the example before, you have seen. So, and then there's of course higher order terms like this. Again, it was just there to introduce some notation. So the this object here is the Greenberger-Horn-Zeilinger state, mentioned even in the Nobel Prize announcement for Zeilinger, of 2 levels. And this here you recognize as the W state. And so this shows to you that the GHZ, so if you divide the whole thing by epsilon, right, it shows to you that the GHZ2 goes to the W plus order epsilon for, this is a big O, sorry, for arbitrary epsilon. Okay. Interestingly, it is not difficult, but the first step of a lower bound technique called the substitution method to show that it without this epsilon that's not possible. Okay. So this is basic, but still kind of like you know, non-trivial. You can try to do it while I'm speaking. If I'm speaking too slowly, it would be interesting. You should do it. So what does this show? This shows that the pre-order of restriction is not closed. Okay, so if I cannot take the limit here of this equation, and then it's still true, because that's false. And so it's not closed, and it calls for then, obviously almost, an introduction of a closure of it, and put that here, and we'll put the closure here. And so we say that T degenerates to T prime if for epsilon there exists some T epsilon such that T restricts to T epsilon, and then T epsilon for epsilon going to 0 goes to T prime. And maybe I should call this T prime, that's more appropriate. So in that sense, then the GHZ2 degenerates to W. We've just seen this, and this somehow completes the classification of 3-qubit entanglement. Because it's so nice and maybe rememberable for you, I'm writing it down. I've shown to you for AB, right? And then you can continue, and here you have the product state. We haven't spoken about that, but I think it's clear. So this is the classification of 3-qubit entanglement that you can find in classic literature or in the Dürr-Vidal-Sirac paper. Any questions? All right. So. Because quantum information theorists, sort of like resource theories, are become fashionable, this here is sort of a resource theory way of summarizing what I've said. T I like to view as a valuable resource, and then restriction is the free operations. And you might replace this by a degeneration here, but let's just, for concreteness, fix it as then we have a unit. Usually have a unit cost in which you pay your stuff. The unit here is the GHZ level R state. Sometimes I'm putting a K here to indicate how many factors we have. It's all resource theory, so K is fixed, okay? So the number of particles here has been fixed throughout. And then this resource, it generates some kind of cost. And what is the cost function? The cost in this case is known as the rank, and that is the minimum of the unit, the minimum of R, such that GHZR is generating T. And there's also what Strassen called the value. And the value is Q of T, which is the maximum of R, such that T restricts to GZR. Okay? So how much does T cost when you gotta buy it on the market, and how much you get back when you try to sell it again? Usually in entanglement theory, we call this like the entanglement cost, and we'll call this the distillable entanglement. Sorry?
Entanglement information. No?
Entanglement information. Oh, because we don't have the asymptotics, you mean?
Okay.
but I think usually in general you call it the cost, but traditionally has been called the value here. This here is known as the tensor rank, or maybe you have seen a different definition for tensor rank before as the number of product components and it write something, but it's just the same equivalent to this. It's easy to see. This here is called the subrank. All right. Maybe as a side remark, I'm not going to dwell on it. If you choose K to be 2, then you of course have matrices, and then the whole tensor thing turns into matrices. These two are the same, and everything will be somehow not too difficult. All right. There is an example associated. You see, these things are just derived from this here. So let me do an example, and maybe the example I'm just going to pencil it into my graph on here. Of course, the rank of the GHZ and the subrank are 2. For the W, the rank of the W is 3. So you see that the rank, because, yeah, okay, and the subrank of the W is 1. And then we have, I think this was already my examples. If you swap it out to degeneration, then the border rank of the W is 2. But everything else stays as it is. All right. Very good. Any questions? This was the first part. I'm maybe two general remarks. I mean, when studying such a resource theory, and we will see others in the coming, there's always two things. There is constructions and obstructions. Okay? There is constructions of restrictions. How do I do it? And you've seen here in these examples the construction and the constructions. And there's the obstructions. I've just stated this obstruction. We can dwell more on obstructions, but and I guess you're familiar with the constructions and obstructions for many aspects in mathematics and also computer science when you have such a setup. So that's just the tensor setup. Tensors are very good at. We're coming to my next part. Tensors are very good at being combined in some way. Okay, so we want to build larger tensors from smaller ones. And how are we going to do this? Obviously with the tensor product. So we're going to tensoring some tensors now. Let's start with an example. Well, if I'm combining two, I need to specify two things now. So T and T prime now will assume different roles. I'm still going to call them T and T prime. But before I was kind of comparing T and T prime, and now I take T and T prime and I'm tensoring them together. Let me do this. And for simplicity of my notation for the example, I will just going to take K equals 3. All right. Now remember my pictures. So that's T, and that's T prime. Now, I'm formally going to define this tensor product now, but it's sort of like clear that I can think of this as, and I'm going to take the time to write it all out. I can think of this as as an element in this space with 6 factors. So I can think of this as a order 6 tensor. Which actually is the way that I've just drawn it. I've drawn 6 dots. And they're just next to each other. Or if you want, you could there are also 6 legs sticking out if you want to think of it in this notation. But I could also do the following. I could group I could group them together, and I could think of this as an order 3 tensor. And my picture will look a little different then, because I have to be a little more precise also drawing it. Let me use a different color for the second one. Because what I'm doing is I'm thinking of these here as the 3 together. Okay, and there's sort of there's fundamentally different ways of viewing this this tensor product. Very often in the literature, this way of viewing it, maybe even we would start giving it a different symbol. I'm actually not doing this here, and we would call this the Kronecker tensor product. Kronecker tensor product. But you see why I'm not going to do it. Because it's obvious that when I present it to you like this, that there's a wealth of ways of doing that in between. I could view it as a 4 tensor by leaving 2 of them open. I could, I could do something like this. Okay, etc. Right? Different ways and different ways in which I could view it. And so it depends kind of on it depends on what structure I want to give you. But sort of like it now this way of thinking about it, it opens something, because we can now take tensors and combine them in these different ways, and I think it's sort of like clear how we can continue. And I want to give a small example and then make a definition. Here's a small example. I could just take this tensor, which would just be the EPR pair of, say, dimension 2. And okay, in my notation, I should have written really, I should have done it like this, right? But that's really commonly done, commonly written like this, I guess, like a graph. Now, if I take 3 copies of it, right? I could either do this, right? Or I could put them like this, or I can put them like this. Okay, this here is just an EPR pair of dimension 8, right? I don't know what that is. That's some 6 tensor pairwise, 6 particles pairwise entangled. And this here is actually the tensor. It's known as the matrix multiplication tensor. For 2x2 matrices. That was one of the reasons that Strassen introduced this a lot of this technology. But you see that how simple it is from once you have the right view now to generate all of these structures. And of course, it's not limited to 3 tensors. Okay. So what do you want to do? I want to now formalize this maybe in some general way. I want to take H in hypergraph, and hypergraph has a set of vertices and a set of edges. And what is a set of edges? So as an edge is just a list, an ordered list of vertices. And I'm also allowing the same edge to appear several times. Okay, so I'm allowing multiple edges. Allowing same edge to appear multiple times in the set E. All right, so example of a hypergraph is of course a graph where I just have where my edges just have always a start point and an end point. And here you see an example of if you now forget that there was tensors behind it, then you see here is a triangle graph with its 3 edges. Okay, this here is also a graph on 6 vertices. Arranged like that. And this here is a graph on 2 vertices with the same edge 3 times appearing. This here is now a hypergraph on 4 vertices with 2 edges, 2 hyper edges, each of size 3. This here is a hypergraph on 3 vertices with this single edge appearing twice. It is convenient now, to really think of this as an ordered list because it allows you better to keep track of things. All right. I guess ordered would then make it a direct graph if I wanted to be precise. All right. Very good. But I think it's clear now that what I can do is I can take a map that maps an edge to a tensor on the edge. And if the edge has, if this has size k, then my tensor here will be a k-order tensor that I need to associate to that edge. So as we've done before here, I have tensors of order 3 and I have edges that have size 3 and I'm attaching it to, I'm associating to them. Okay, so for every edge, so I start with a hypergraph to every edge or every hyperedge, I associate a tensor, and now I'm gluing them together. Right, I go over all edges in my hypergraph and I take my edges. But now I want to view it as a certain tensor of a certain order. So what I want to tell you is now this. I want to tell you how its structure of tensor factors is. So I'm thinking of this as lying in, and I'm starting with now the vertices. So for each vertex, I'm telling you now the incoming spaces. So for each vertex, I have a bunch of spaces, and maybe you can see it here. For this vertex, there's only one space, namely coming from that edge. For this vertex here, I have 2 spaces, one coming from here, from there. So I'm going over all of the edges such that the vertex is in the edge. Okay? So I go over the vertices, so I take that vertex, and then I'm looking over all of the edges. and then I'm collecting the space. So I'm going for the C that has the dimension that's associated to that edge and that vertex. Okay.
If you thought of these as polynomials,
Oh.
then you could add polynomials of different.
Yeah, you can think of things in terms of multivariate polynomials. It's not my favorite way of doing it, but then you would basically, I think that then what you would do is you would take an inner product with a product that with sort of a product tensor that's like a simple tensor that has variables in it, and then it will turn it into a polynomial that we could study.
Yeah, you could just keep what you wrote in the beginning, right? So you keep the superscripts. Bracket 1 and bracket 2 on the first board. There you wrote t equals sum.
Yeah.
You just keep the superscripts, and then you remove the tensor products, and then these you call the ei1 superscript 1. You call that's a variable.
But, yeah.
Okay. Now, I like to call this an entanglement structure. And actually, there's I think 2 papers in literature that call it the entanglement structure. If you're just looking at GZ states and EPR states, I think Jeroen and I, we called it tensor graph tensors. We call it, which probably maybe we should call hypergraph tensors, which I thought was a nice way. But then, of course, there's these graph states in quantum information, which are different. So it's maybe a bit more confusing. So maybe it's better to call it entanglement structure. We'll see why I later prefer that word as well. All right, very good. Okay, you're on board with me that this was just a formalization of what you had intuitively understood when I glued them together like this. Okay, there was no magic beyond. Was just trying to formalize them. Mathematics sense. There we go. Maybe I can already now, sort of like, I guess, you know, before we've talked about this restriction order, right? But now to every, so now think, and so of course I introduced it in the way that I told you that for every edge you can choose your tensor T. But just imagine that, you know, you want to make life a little simple for you. Then maybe you want to, maybe it's a 3 uniform hypergraph, so all edges have size 3, and you always associate the same T. Okay, to every edge. Makes sense, right? So then you know, life gets a little more easy. Then somehow I could use this notation, right? Or you know, actually I used it already, even though I had chosen a different one. So, but now you can think of this actually being the same. So then of course when T restricts to T prime, that would be one way. But then I like to say I roll it out on this hypergraph. And then I can ask this question. You know, I can ask this question, but I can roll it out in a hypergraph and ask this question. And of course, if T restricts to T prime, it's easy to see, you know, I could call it lemma, that this restricts to this. Okay? But the converse is not necessarily true. So, you know, we can try to study this here in its own right. We can try to study this restriction in its own right. and I think there is, I want to, there's 3 natural settings, I think, which to study it, and I'll give you these 3 settings. Each of them non-trivial. I call the first one independent. I'm saying non-trivial because at first it might seem trivial. So, and here is my and just for varying, you know, I'm going for triangles to squares now. Guess maybe that brings Marius awake. Maybe it wakes you up again. So I'm going to. Sorry, Marius. It's just making a joke. So. So why not having them independent as before? But now thinking of this here actually as being large, as being n, okay, and like growing n. So this is here is a, you know, this is a tensor. The order is 4n. Then I could do this, which maybe seems, you know, most natural to physicists. I can put them on a lattice. Right? This here is now one vertex, and I can continue my lattice. So this would be an n tensor if you put it on the torus and have no boundary condition. And of course you can choose a different type of lattice. It just chose the square lattice, the only one I can draw. And then there is the last one, I'm going to squeeze in here, which I actually like to call the Strassen way of doing it. Strassen way is the thing that where I put them on top of each other, okay? Maybe I think you understand what I mean. Okay, so here is, I've looked at it as a 4 tensor. Okay, so this is 1, 2, 3. These are 4, the 4 vertices, and I just stack them. I stack them on top of each other like this, and I identify them like that. All right. Now, this one here probably, I mean, as mentioned already, is the most familiar one. And if you choose as your tensor not like, say, a GHZ state, but you use, say, EPR pairs, then this is known as the PEPS states, projected entangled pair states. You know very well. People have studied it also with GHZ states on, and right. And this here is the most commonly studied now in algebraic complexity theory in this matrix multiplication problem. I can dwell on it more, but I really like to convey the message that we have this choice of like going from here to here. And that we can view all of it in a unified way. So in particular, we could consider a family of hypergraphs. So this was one family, another family, a third family. We could consider other families of hypergraphs, where n is size of the edge set. And we could ask, we could study when is t h degenerates to t prime, meaning when is it true that and this here would be the first thing that you write down. When is it true that this that we have this asymptotic notion that like on a lattice I can do it. So then I have to be able to do the conversion individually. But it turns out this is not the right notion. You have to put the fudge factor in. You have to smooth somehow the left-hand side, and you have to say, well, I'm allowing a little bit of a fudge factor. This is actually really small. I'm allowing also a direct sum here, and there was a lemma. Maybe if I have time, I can tell you about the lemma. But there's a lemma that makes it precise, and then because of this order n, you can sort of really understand the asymptotics, and you don't need to have a hard kind of like it has to hold for all of them, but it only has to hold in the right way. So in some sense, that's a smoothing, a smoothing operation on what you really want to say. So I'm somehow proposing that we should study this, and want to show you a couple of examples now at the end of my talk, in which we have studied this in the past, and how we're thinking of this. Okay, in these three examples, and maybe I start with the Strassen one. So Strassen introduced this notion here already, and in the Strassen case, of course. So the first case would be the Strassen case, in which you ask, for the Strassen thing, when does this bigger than that? And now I can put Strassen here. And Strassen has this amazing theorem, and the theorem says that it gives a complete classification of this. He says T asymptotically restricts as a notion. No, it's not Strassen restricts, but asymptotically restricts to T prime. Maybe I should say that here. So yeah, asymptotically restricts. And why do I say smooth? So the smoothing operation here is a very good operation, because when you look at the asymptotics, it doesn't actually matter if you define it with restriction or with degeneration. So it smoothes out some of these differences. And so therefore it makes sense to just define it in the way I did, and not, it would be the same if I were to use degeneration. So T asymptotic restricts to T prime if and only f of t bigger than f of t prime for all Strassen f's. And what are Strassen f's? These are functions that, if they're monotone under restriction, that are normalized on the GHZ state, they are multiplicative, and they're under tensor product, and they're additive in the direct sum. So this was Strassen, and some years ago Peter Franer and myself and Jeroen Sauter, we gave a construction for some of those functions, and the functions are the they're the exponent of something, and And this is actually something that is not so hard for us to understand from a quantum information theoretic point of view. But maybe I'm just writing it down and so basically I'm taking T, I'm restricting to T prime, and I'm maximizing the average local entropy. Okay. So I think of T as a quantum state, I go for the 3 reduced density matrices, and I maximize the phenomenon entropy, the average local phenomenon entropy. So this would be theta 1 h of, maybe I'm writing T a prime it's not maybe I'm writing 1 here. Yeah. So this is one result for this direction. There is a fun result for the second direction I want to flash. Since we'll put that down. And then for the last one. So for this independent thing, as I said before, well, it looks kind of trivial, but what can happen there is that you remember the rank function. You remember like the W state, and the W state has the rank of W is 3. And now, and what was the rank? The rank was the size. You know, that meant that you needed 3 to restrict to this. And now I'm giving you 2 copies, right? But on the independent W, okay? Just like tensor product, right, next to each other. It's a 6 tensor. And obviously, by just repeating this construction twice, you would. So if you have 2 GZ states tensor together, of course, can restrict to this. But if I'm interested in the rank, now as a 6 tensor, the question is how many levels do I need of a GZ state on 6? Of course, I can, with 9 levels, I can think of them as being 3 times 3. I can use the first 3 to generate this one and the other 3 to generate this one. But it turns out that you can do better. So actually, it turns out that you can do it. There's a shortcut here that you can do it with 8. Okay? And so what does it mean? It means that this asymptotic rank function, okay, so the rank as a 3 times n tensor of these n copies, it makes sense, and it will be non-trivial to study this asymptotic rank function, which we gave this notation. So I can ask now, when I take n copies, how much do I need per copy of rank in this? And so we studied that, and I can give you the references later for the 2 papers. But for this particular value, the number is actually 2. Okay? So you can really gain from 3 to 2 in this way. anyway, to all of these constructions, there are also obstructions. I think my time's kind of up. There should be some questions. And maybe before I open for questions, I want to say one thing about this lattice thing, which is in the paper, is that what you now can use this for is that if you have some genuine tensor network, it's always presented on top of an underlying entanglement structure, either PEPS or MPS, right? The MPS would be the line graph, or PEPS would be the lattice of EPR pairs, or some other. So it's always presented on top of some, as a restriction of some hypergraph tensor. And of course, if I now understand how this can be transformed, or maybe better this way, how this can be transformed into this, then when I understand this transformation here, then I will be able to take, say, even numerical code that was designed for this one, and map my tensor network to this one and work with that new structure. And I think this is a sort of maybe a different view on tensor networks and how we can work with that. And we give some examples of constructions and also obstructions for these transformations. And I hope very much we can do more on that. This sort of closes my talk. I hope I conveyed to you that that I like to view tensors as a resource, but in this combined way of rolling it out on a hypergraph, on a tensor network, giving access to both the algebraic complexity side, so putting them on top of each other, and also putting it on the lattice, so in this unified perspective. What is the advantage of doing that is, of course, it allows you also to transfer now techniques from one to the other, in particular between algebraic geometry and maybe tools from condensed matter. The title of this workshop has combinatorial in the title. And what the connection to combinatorics is, that comes in through the view that some people use on certain combinatorial problems, say the famous cap set problem or sunflower problems and other problems that pop up either in constructions or just in combinatorics straight. And so if you want to, if you're interested, I brought this game set, which is directly related to the tensors and how we can solve combinatorial problems or understand them with these tensors, and we can play tonight. Well, thanks for your attention.